The origins, history, and structure of the universe were seen as religious and philosophical matters until the 16th century. Everything was thought to revolve around the Earth and humans. But in 1543, Nicolaus Copernicus shattered this Earth-centered illusion. About 100 years later, Galileo Galilei refined the telescope, pointed it towards the sky, kick-starting observational astronomy, and strongly supporting Copernicus's theory of Earth orbiting the Sun. Gradually, scientists no longer relied on faith to solve but used scientific instruments to see what the universe looked like and how it evolved. About 100 years later, Isaac Newton explained a series of previously unrelated phenomena in heaven and Earth using universal gravitation and the inverse square law of distance. He also calculated the period of the planets around the Sun, making astronomy, just like other scientific training, no longer a debate about faith, but a question of evidence and theory. When astronomers realized that humans could not be the center of the universe, there was no reason for scientists to believe that our place in the universe occupied a very unique position. Similarly, there was no reason to believe that the moment we are in is very special. This is known as the cosmology principle. The universe should always exist as it is, with no beginning and no end. Newton's mechanics dominated the development of physics and astronomy for over 300 years until they were revised by Albert Einstein's theories of special and general relativity between 1905 and 1915. After Einstein published his gravitational field equations, he of course also pondered the question of the universe, but found that the solution to his field equation could not be a static universe. To fit with the universe view at the time, Einstein, the pioneer of the modern physics revolution of the 20th century, succumbed to the consensus and modified his equations to get a static solution. As early as 1718, British astronomer Edmund Halley found that 3 bright stars were no longer in the positions confirmed by ancient observations, seriously questioning the assumption that stars are in fixed positions. If stars can move freely like normal physical objects, then is the universe static? Between 1922 and 1924, the Russian mathematician Alexander Friedmann assumed that the distribution of objects in the universe is uniform, solved the general relativity field equations, and found that there are only 3 possibilities for the distribution of these substances in space over time. From the beginning, space slowly approaches a constant value as time increases. It will continue to expand forever. It expands for some time and then begins to contract. In 1927, Father Georges Lemaitre, a professor at the Catholic University of Louvain in Belgium, also independently discovered the Friedmann solution, but he was more interested in its physical significance, predicted the actual expansion of the galaxy universe from it, concluded that the retreating speed of clusters farther away from us should be faster, but no one cared about the revolutionary conclusion. Einstein accepted his mathematics, but refused his physical explanation. In 1929, the American astronomer Edwin Hubble analyzed the measurement results of the spectra of light from distant star clusters and found that their frequencies systematically shifted to the lower redshift, and the shift value increased with the increase in distance from the planet to us. Distant star clusters are moving away from us according to certain rules. The farther away from us, the faster the retreat rate. This is called the Hubble-Lemaitre law. The inevitable conclusion is, the universe is in a state of expansion. This completely unexpected discovery changed the entire face of the study of cosmology. Unfortunately, before Hubble's death, astronomy was still considered within the realm of religion and philosophy. As a result, he never received the Nobel Prize. An expanding universe is a changing universe and therefore should have a life history. In 1931, Lemaitre began to trace the footsteps of the universe, leading to his so-called primeval atom hypothesis. He published a short 457-word article in Nature stating, "If we go back into the past, we must find fewer and fewer quanta, until we find that all the energy of the universe is contained in a few, or even a unique, quanta. If the world began with a single quantum, then the concepts of space and time would have no meaning at the beginning. We can imagine the beginning of the universe in the form of a unique atom, the atomic weight of which is the total mass of the universe." The atheist cosmologist Fred Hoyle, who did not believe in the primeval atom hypothesis, sarcastically called it the Big Bang in 1949. Unexpectedly, this term was widely accepted by scientists, who referred to Lemaitre's cosmology as Big Bang cosmology. In December 1979, Alan Guth, a professor at MIT, wondered if his research on the supercooled Higgs field could also apply to cosmology. Guth's research suggested that if the early universe was filled with a Higgs field known as an inflaton, This inflaton could be trapped in a supercooled state of high energy and instability as the universe expanded and cooled. This state, due to its negative pressure, could provide a strong repulsive force, causing a moment of enormous expansion, the cause of the Big Bang. However, because this state is highly unstable, this rapid expansion only lasted for about 10 to the power of minus 35 seconds. But during this time, the rate of expansion of the universe increased rapidly. After this, the rate of expansion of the universe, due to gravity, returned to its normal decreasing state. This rapid acceleration of expansion not only explains why the current universe is so uniform, it also tells us that the universe we observe today is a very small part of the whole universe. This also explains why the universe we observe today appears flat, just as a small area on the surface of a large sphere appears flat. This accidental discovery quickly solved the three major mysteries of the Big Bang theory. About 10 to the power of minus 35 seconds later, the Big Bang stopped, and the inflaton released its excess supercooled energy, creating the matter and energy we see today. Scientists call this modified Big Bang theory, inflationary cosmology, and the original Big Bang theory, standard cosmological Big Bang model. A universe that Big Banged from a unique atom should have boundaries, and a universe with boundaries should have edges. But if there are edges, there should be a very unique center point. Doesn't this violate the cosmological principle? And what's outside the edge? If it's space, it should be Big Bang, it should be part of the universe, so the universe should have no edge. A universe without boundaries doesn't have to be infinitely large. Einstein's 1917 universe was a finite universe with no boundaries. If the universe's geometry is flat, it can't curl back, then the universe should be infinitely large, without boundaries. Nevertheless, the expansion of the universe continues to create space, so space becomes more infinite over time. We understand expansion from an external perspective. Like watching a balloon inflate, we see its volume getting larger and larger. But there's only one universe, we can't stand outside of it. And if the universe is infinite, no matter where we are, we'll feel like we're at the center of expansion, just as any point on a sphere sees all other points moving away from it at a speed proportional to their distance. Moreover, standing on the other side allows us to see the expanding space outside the balloon. We can measure the motion, speed of any point on the balloon to the Earth during expansion. But if we're in the expanding universe, we obviously can't see the expanding space outside the universe. No, wait, the universe is infinite. How does it have an outside to expand? Of course, it doesn't. So modern physicists think that space, like the surface of a balloon, is expanded, not moved, created. The spatial distance between two objects increases due to expansion, not relative motion. Gottfried Leibniz finally triumphed over Newton. Where there is no matter, there is no space, space does not exist at all, and space is just a language used to describe the relative positions of objects. Therefore, the systematic movement of distant star clusters measured by Hubble away from us is not the result of the movement of star clusters. The star clusters are not moving in Newton's absolute space. If the idea that space is manufactured is hard to accept, believing in time is much easier to understand. Think about it. Now does not have tomorrow. Tomorrow appears in the now of tomorrow. So, tomorrow is manufactured. Time is expanding towards the tomorrow that does not exist now. There is no boundary between now and tomorrow, so time should have no edge. There is no question of what is outside the edge without the edge. Therefore, the expansion of the universe not only created space but also created time. The first chapter of Weinanzi in the Western Han Dynasty calls the four directions, Yu, and the past and the present, Zhou. This sentence clarifies that Yu is space, Zhou is time. The universe is space-time, and the history of the universe is the history of the manufacture of space-time. If time is created because of the Big Bang, how old is the universe now? The ratio of the speed and distance of distant galaxies estimates the current age of the universe to be 13.8 plus or minus 1.0 billion years. In 2013, the European Space Agency's Planck Space Telescope drew a detailed map of the fluctuations in the cosmic microwave background temperature, estimating the age of the universe to be 13.82 plus or minus 0.05 billion years. On March 30th of last year, a group of astronomers led by Dr. Brian Welch from Johns Hopkins University announced the discovery of the farthest and earliest star in history, a point of light emitted 12.9 billion years ago. Hubble's discovery of the systematic redshift of galaxies finally allowed us to resolve the conflict between Newton's infinite universe theory and the religious finite universe theory. At first, people thought that the redshift effect alone was enough to explain why the night sky is dark. Light from stars in distant galaxies will be redshifted out of the visible light range to longer wavelengths. However, the current consensus is that the finite age of the universe is a more important influence. Even if the universe is infinite in space, due to the finite speed of light and gravity propagation, photons or gravity from distant galaxies have not had enough time to reach the Earth. If the current age of the universe is 13.8 billion years, then we will not feel the light or gravity from outside 13.8 billion light-years away from the Earth and believe that the universe is finite. We call the universe within this sphere with a radius of 13.8 billion light-years the observable universe. The number of stars within this cosmic horizon is about 200 trillion, which is too few to make the night sky bright or to tear the Earth apart. Also, if Newton knew at the time that the universe was expanding, he would not need an infinite and eternal, divine power to prevent nebulae from being pulled together. If space-time was created by the Big Bang, then there was no space-time before this. No space-time? So where did this Big Bang take place? To explain that if there is a center of the explosion, it violates the cosmological principle. Some theoretical astronomers even proposed that the Big Bang happened everywhere at the same time. But isn't everywhere space? Isn't this the paradox of which came first, the chicken or the egg? Although philosopher Jean-Jacques Rousseau believed that the real world has an end, the imaginary world is infinite, when writing this section, I am still overwhelmed. Paul Sutter, an astrophysicist at Stony Brook University of the State University of New York, said at the end of his article, "What's outside the universe?" published on February 25 last year. If all this sounds complicated and confusing, don't worry. This is one of the strengths of modern cosmology. It enables us to study things that are hard to imagine. I guess all we can do is accept these paradoxes and strive to adapt to them. Just like the gravity mentioned earlier, wasn't it initially considered to be magic, mystical, unscientific? But now no one doubts the existence of this force. Similarly, aren't there many strange views in modern physics, relativity, quantum mechanics, that violate the logic of our daily lives? In 1998, Saul Perlmutter from the University of California, Berkeley, and Brian Schmidt from Australian National University announced that data from Type Ia supernovae showed that 7 billion years after the Big Bang, the expansion of the universe accelerated again. Adam Rees from Johns Hopkins University affirmed these observations in 2006. This discovery rewrote mankind's view of the universe's evolution, leading the Nobel Prize Committee to award these three scientists the 2011 prize in physics. Just as physicists finally understood the cause of the Big Bang, and that the expansion of the universe after it should gradually slow down due to gravity, why is its expansion now accelerating again? Newtonian gravity only has attractive effects, so to explain this accelerated expansion, it seems that we can only turn to the cosmological constant in Einstein's modified equation. Indeed, Perlmutter and Schmidt thought, after the Big Bang, the universe continued to expand due to the momentum of the Big Bang, but due to gravity, the rate of expansion will become slower and slower. But if there is Einstein's cosmological constant, since its repulsive strength does not decrease as the universe expands, there will come a day when it will overpower gravity, making the universe's expansion rate accelerate again. This day happened around 7 billion years after the Big Bang, which they discovered. But what exactly is Einstein's cosmological constant? Nobody knows, but it isn't ordinary matter, otherwise, it would have been discovered long ago. Therefore, scientists call it dark energy. Physicists and astronomers are working hard to find this monster that fills the universe and must have negative pressure. Most astronomers today believe the universe is flat, is expanding, has no boundaries, and is infinite. The successive discoveries of black holes and gravitational waves have solidified the theoretical status of general relativity in current universe research. The universe we see now is just a small part of the entire universe. Those farthest galaxies from us 13.8 billion years ago are now actually 46 billion light-years away from us due to the accelerated expansion of the universe. It's hard to imagine what an infinite space with no edges looks like. How can space be continuously created there? These incomprehensible, paradoxical logics might be what Bertrand Russell meant when he said that the idea that things must have a beginning is actually due to the poverty of our thoughts. Or what Max Planck said, science cannot solve the ultimate mystery of nature because, in the end, we are part of the mystery that we are trying to solve. This makes me think, artificial intelligence is created by humans. Can it, like us, create Newtonian mechanics, relativity, and quantum mechanics? Or even surpass humans to create a cosmological view without paradoxes?